So in cooperation with Centralkommunernes Transmissionsselskab, we did a proof of technology in which they wish to identify if already existing data is sufficient to be able to predict the optimal supply temperature in their transmission system. So just to set the framework, this is only the proof of technology. We have not yet put this into production. We're going to do that after this summer vacation. So what I'm going to talk about is how this project came to life and how we succeeded with something that all odds were against us. And this is the proof of technology part that I'm going to talk about. So when we do a proof of technology in neurospace, we do it in a 1-month high-intensity camp called an AI camp, which consists of mainly two things. The first part is the knowledge sharing, and I cannot emphasize this enough. With 5 years of experience working with and delivering machine learning, this is key for success in machine learning. So the knowledge sharing is, the objective is to create a common language. So they need to understand my domain, I need to understand their domain. And if we don't understand each other, then the success of the project will fail on this. So when I say to Centralkommunernes Transmissionsselskab that this is a supervised learning algorithm, so I need a label, then they understand what I mean. When I say I need features that can help me predict this, then they understand what I mean. They also learn in this knowledge sharing part, where we create a common language, that you can almost never get 100% accuracy. That's just not sufficient. So they get to understand what machine learning is and what it's able to do. At the same time, I get to understand their domain, which is district heating and transmitting district heating. So when they say that flow can only reach a certain temperature, because if it gets higher than that, we will create a water hammer in the pipes, which basically means that you damage the pipes from the inside, then I need to understand that, because otherwise I cannot do a proper data analysis, which is 99% of success of machine learning algorithm. So I need to understand basically how things work, how things are geographically located when I look at the data, and I need to understand what looks abnormal and what is perfectly normal in the data set. So when we have created this common language, we can together work in a team to create this readiness assessment, which basically is the proof of technology. So this is a 1-month high-intensity camp. So in the data journey part, we always ask our customers to define the objective of the goal as a user story. And they wrote it as Centralkommunernes Transmissionsselskab. We want to predict the true supply temperature 12 to 36 hours in advance, such that we can ensure the best electrical efficiency as well as our service obligation at the lowest possible temperature. So one thing I really love about user stories is that we create a common understanding of the objective of this project. Normally, it will not say a Centralkommunernes Transmissionsselskab, it will more say a specific department or specific person, so I also know who my solution is created for, so I can talk specifically to them and make sure that the solution fits their needs. Another key thing that I get is that I need to be able to predict this at least 12 hours in advance, and preferably 36 hours in advance. And the final clue that I get from this is in the such that, where they say that I have to create a model that predicts the lowest possible temperature, but not such that it interferes with their obligations to this service obligation. So they are critical infrastructure, which means that they actually have a service obligation. They are obligated to deliver heat to the customers, which means that it's not possible for them to deliver at too low temperature. So I know already now that I have to predict at least 12 hours and that my model should not underestimate the supply temperature. So if we just talk about, just a few minutes, why this is important for companies like Centralkommunernes Transmissionsselskab or in general district heating. One thing, if they know it in advance, is that they can use that knowledge to actually create the best mixture for generating the heat. If they know what kind of mixture they can use to create that, to gain that certain supply temperature, then they can also prepare maybe to get the most green heating mixture. And one other thing in talking about the green district heating is that they can actually also reduce the return temperature. So if, just very basic, when you deliver a supply temperature, you have a customer demanding a certain temperature, and if everything was just the perfect world, you would just deliver exactly that temperature, and then everything would be happy, or everyone would be happy. But if you deliver 10 degrees higher than that, that 10 degrees higher, that difference will actually just go directly into the return temperature, and that would just be a waste. So that means that you use energy, and you create the heat that you actually never use for anything. It will just be a discarded waste in this situation. So if you can reduce the difference between the true temperature and the temperature you deliver, then you will actually make a greener district heating. If you can create a greener district heating by reducing the return temperature and reach a closer gap between the optimal temperature and the temperature you deliver, that will also create a cheaper district heating for the customers. So there is quite a lot of reasons why this is interesting for a company like Centralkommunernes Transmissionsselskab, or in general anyone within district heating. So I think almost everyone here has district heating at home. But district heating is this thing that we actually don't really think about in our everyday life. If you think of them, it probably means that you're actually upset because you had a cold shower this morning, or it is too cold in your home. So the perfect world for district heating is actually that you don't remember that, you don't think about them. You know they exist, but you don't really care, because that means that they obligate to their service obligations. In the moment you care about their existence is because they are too expensive, or they don't deliver this heat required or requested from you. So that means that probably all of you know district heating exists, but maybe not all of you actually know what district heating is. So just very basic understanding of district heating. It used to be like you have 1 unit of fuel, 1/3 is used for creates electrical energy, and 2/3 creates thermal energy. The electrical energy, of course, was used to create energy or electricity, whereas the thermal energy actually was just a waste product from this process in power plants. And then back in the 1900s, we had this clever people here in Denmark who said, we have this huge amount of heat, why don't we utilize it for anything? And that's the very beginning of district heating. This waste product that was a huge amount of heat was actually just distributed in pipes to our homes and made sure that we could have a warm bath and a home with a warm house, or a house with warm. So it can come from a variety of sources. The first one is from overproduction in wind turbines. They actually create quite a lot of heat. This heat can just be distributed into the system, and then you will actually use this overproduction of heat to help heating up your homes. Another place is from production facilities. If a process, for instance, shows, a process where you boil something, you will create quite a lot of heat, but that process will the high temperature that you create will just be a waste product for the main thing that you're going to create. If you attach that specific process to district heating, then that will also contribute to warming up your homes. So in general, again, it's just a waste product. It can also come from data centers, which is quite new here in Denmark, but data centers produces quite a lot amount of heat. We can also use that for district heating. And in general, everything that produces heat as a waste can be used for district heating. So it's quite complex because you can actually get this heat from a variety of sources. So if we look into Centralkommunernes Transmissionsselskab, they are transmitting district heating in 5 municipalities, which they are owned from. It's Tårnby, Copenhagen, Gentofte, Frederiksberg, and Gladsaxe. And just to give you an idea of the challenges, if we go back to the very specific project that we had, I'm going to divide them into the 2 domains. So we have district heating and we have machine learning. And sorry for that. One thing which I already mentioned is that heat can be produced from a variety of different sources. So that's one thing that I have to take into account when I create my model, that they actually can be distributed from a variety of sources, which creates a different amount of heat. Another thing is that this heat can actually be distributed from different heat exchangers and delivered into the network. So in this network, we can have different places where heat actually comes in, and that gives a huge amount of complexity for this project. If we look into Centralkommunernes Transmissionsselskab, just to give you some numbers and idea of what they are, they deliver heat to, or district heating to 250,000 homes in Copenhagen area. And to do so, they have 54 kilometers of wiring harness, in which they have 4 booster pump stations. And these booster pump stations help you to make sure that in this long line of wiring harness, they actually can keep the temperature high. Then they have 14 reserve capacities and 31 heat exchanger stations. In 2021, they delivered 18,718 terajoule of heat. So it's quite a lot. This is another geographical example of how the network looks like. So as you can see, CTR is located in Copenhagen. You also have HO4 there, and VEX is also located there. If you go into this varmelast, if you live in Copenhagen, you can actually see where your heat is coming from. And just to give you an example, heat can be derived from waste-derived energy plants, but it can also come from these 14 reserve capacities, and they include wood pellets, gas, oil, and electricity. So that's the amount of different sources that we can use to create this heat. Another limitation is that there are natural hydraulic limitations in their system, in their pipes. So the temperature can only reach a certain level, pressure can only be at a certain level, and of course, as I already mentioned, flow can only be a certain level, because otherwise it will create a water hammer. And my model needs to learn this. It needs to know that it can never reach a certain temperature or a certain level, because then we will damage the pipe and it's just not hydraulic possible. So my model has to learn these hydraulic limitations. As they have a service obligation, it is not sufficient, and my model is not allowed in any means to deliver or predict a heat that is below the optimal supply temperature, because that means that they will deliver insufficient heat, creating cold water in the showers in the morning. When you look at the customers, there are certain places in this wiring or in this in their pipes, where in the network, where you will see that some customers require a certain temperature. And the customer requiring the highest temperature will sort of set the standard for what temperature you have to deliver. So even though you could deliver 97 degrees as a supply temperature in the pipes, satisfying everyone but that specific customer, you will have to deliver to that customer demanding the highest, which might be 108. So that's another challenge that you have to look into. There is specifically two seasons in this where this project is very, very interesting for district heating or Centralkommunernes Transmissionsselskab in this case, and that's in spring and in autumn, because Danish weather is highly unpredictable in that period of time. So you will see that one day you have sunshine, you have almost no wind, and you have plus 15 degrees, and the next day you will have snow, you will have skies that you will not have sun, you will have cold wind. And those two different types of weather actually require quite a lot for those who have to predict the optimal or the supply temperature that they should deliver. If it's sunshine outside, they can actually go with a very low supply temperature. If it's snowing and it's very windy, then they have to increase it. And this can be within a few hours that they have to actually increase this level. So during specifically spring and autumn, this is very interesting for them to have a model to help predict what's going to happen. So of course, the weather is a key feature for me as well. So if we look into machine learning, the challenge for this project, this is a regression or a forecasting problem which lies under supervised learning. And that means that I need a label. And my label has to be representative for what I'm looking at. So I need historical data that shows me what is optimal supply temperature. The problem is that, as I said, they have a service obligation, which means if you look in the historical data, you will actually see that district heating tends to deliver a too high temperature because they would much rather deliver a too high supply temperature and make sure that they obligate to their service obligation than they will risk having a too low temperature. So that means my historical data has quite a lot of timestamps where I cannot see the optimal because it's non-existing, because you would much rather risk having a too high temperature. And that's one of my big problems when looking at machine learning, that I need to see it in my data because I need to supervise my model for it when I train it. So one of the big discussions we had for a really long time with the domain experts in Centralkommunernes Transmissionsselskab is what is optimal. Can you show me some timestamps where I can see this is optimal? Can you give me a rule so I can find it myself? Because if I can't see it in your data set and you can show me, then I am not capable of supervising my model to actually learn what is optimal supply temperature. And that was one of the biggest conversations we had during this 1 month. That was defining this label. I need to know what optimal is so I can train my model on the optimal supply temperature. So if we look into the solution, we had only 2 years of data, and that's because they have more data, but district heating moves quite a lot. They change all the time. They get new cities or new district heating gets attached, or something that makes that the network does not look as it used to. And that happens all the time. And that means if I go back more than 2 years in this specific problem, that data doesn't represent how the real world look like today. And that means that I was only capable of having 2 years of data to look at. Some of the features we used were pressure and temperature, both the supply temperature, but of course also the outside temperature and flow throughout the entire network. And of course we also used the timestamp, because the timestamp was a key value for actually knowing what is going on. As many of you probably do, you take a shower in the morning when you wake up, which means that there is a peak at that specific point where they actually need to produce more heat. One thing that there is with district heating, and that's every single company that I have worked with within district heating, is that they have actually very high data quality, which is amazing when you work with machine learning, but they don't have much abnormalities or sensors that freeze or anything. So the data quality was really high, which again, if we could find the optimal, then I knew that we were able to actually create this machine learning model. So as I said, we had some difficulties talking about what is optimal. And we had quite a lot of discussions with the domain experts about, well, how do you know if you deliver optimal? And then we had these discussions. And they said at some point, if the world was perfect, we will just deliver the highest temperature as the customer defines it. So the customer demanding the highest temperature would just be the temperature we deliver. But we cannot always do that due to the hydraulic limitations. And that made us create this hypothesis that either you deliver the optimal temperature or you reach one of your hydraulic limitations. And that actually, based on this ping pong between the domain experts and our data scientist experts, we were able to create quite a long if statement, and everything that came through that if statement defined what is optimal supply temperature at the given state. So the data set was significantly reduced. We were very much below 10,000 observations. So if we look at the models, we did 2 machine learning models. The first one predicts the optimal supply temperature. And I unfortunately have to anonymize the timestamp and the temperature, but as you can see on the x-axis is a timestamp, on the y-axis is the supply temperature. The orange line is what they delivered, and the purple line is what my machine learning model predicted. Even though my machine learning model predicts this up and down temperature, if you look 12 hours in advance, that's the only thing I was able to do. I did 12 hours prediction because I had such a little data set. So even though my model has these up and downs, they will just look at the highest temperature my model predicts, and then they will put the temperature to that. They do not every hour turn the heat up and down. That's not doable. So they will just look at what's the highest, and then they will look into that. So this machine learning model was trained on the optimal data set, which was very, very small. And then I tested it on everything else. And then we agreed with Centralkommunernes Transmissionsselskab to test a very specific 14-day period in spring, because in the data analysis section, I could see that there was a very high gap between what was defined as optimal and what they delivered. So we had this hypothesis that in this period you were actually able to reduce the supply temperature significantly. So the only thing I can do is that I can say, okay, I can see my model predicts a lower temperature, and I had one point where I could see that we actually reached a hydraulic limitation on a pressure. And I was able to see that my model predicted the exact same temperature as they did, so it did not underestimate the temperature. But that's where my knowledge of their domain goes. I cannot say if this model is good, if it's valid. So those 14 days of test period, I sent to their domain experts. And then, of course, we asked them to verify, does the model underestimate anything? Has it learned anything? Do those values that the model predicts even look like optimal? And then they verified that it does indeed look optimal, and they believed that they actually could have reduced the model to those values. So on average, on those 14 days test period, we were able to actually optimize the supply temperature with 5.4 degrees, which means that they could actually have reduced on average the supply temperature with 5.4 degrees in just that 14-day period. So if we look at the machine learning model 2 we actually made a model that looks into these hydraulic limitations, and just for this proof of technology, we only looked into one specific limitation that they have, that we had to create a model for everything if this is going into production. So the model looks like this, and what you see is it actually just predicts the gray predictions that you see. It predicts 24 hours in advance, and the gray dots that you see is every single line of them is the temperature lowered 1 degree. So we could see what happens with model 1. If it predicts a certain temperature, we could put that temperature into this machine learning model and see if we reach this hydraulic limitation. So that's our way to make sure that even though we had a very small data set in the first one, we do not want to interfere with their service obligation, and this model has to help us make sure that we do not underestimate the supply temperature. So if we look into the user story again, they said very specifically, such that we can ensure the best electrical efficiency as well as our service obligation at the lowest possible temperature. So the first machine learning model I showed you actually predicts the lowest possible temperature, and the second machine learning model we created makes sure that we do not affect their obligations to this service obligation. So those two models together actually make sure that we can satisfy this user story as they created it. The first model only predicts 12 hours in advance, and the second model right now predicts 24 hours in advance. Any questions so far?
No questions?
No? Well, then I will just continue with the key takeaways. So one thing that I learned, so I have been in neurospace for 5 years, and just so if you don't know neurospace, we work with quite a lot of different companies, and almost all companies that I have worked with has this strategic goal of big data. And every time that we talk about using data for machine learning or for any other kind of data analysis, then they say we cannot do that yet because we have not enough data. And then my initial question is always, when do you know you have enough data if you don't analyze the data? And they actually never answer me because they don't know. So just to be sure, right data is not big data. You don't need big data for machine learning projects. You need representative data. And I had less than 10,000 timestamps that I could use for my machine learning model, but they were representative for the objective of predicting optimal supply temperature, and they were also enough that I could create a pattern, because that's really what you do with machine learning. You have to be able to distinguish something with patterns. So in the moment that you can see representative data and you can see this pattern, you can see that there is a pattern in your data, and then you can actually start doing machine learning. You don't need big data. You don't need 100,000 observations. You just need representative data, and you need the right data. That's one really key point that I hope you can take with you from today, if any of you work with machine learning in any sort of way. Another thing is that this model, of course, does not predict 36 hours in advance. It's not possible because I didn't have enough for the machine learning model 1 to actually create that opportunity. I can only predict 12 hours in advance. But thankfully, there is this machine learning flywheel, which means that in the beginning, it might run very slow because we just created a model and the model was only trained on that data that we had historically. But when they put this model into production and it starts to predict and they start to use that to actually lower the temperature, that means that I will get more relevant data that is representative for this case, because we will have more data that is close to optimal supply temperature. That means that I will get more data to train my model on. I will get a better model. It will create better predictions. And then this flywheel starts to roll faster and faster and faster. And that's the beauty of machine learning. Right now, it's going very slow. When we have implemented, it will go really fast. Just to give you an idea, this is our 30 days of AI camp, so the proof of technology that we do. This knowledge sharing part is key for the success of any project, and specifically this one. If I was just sitting in my domain and looking at that data, I would never have been able to pinpoint what is optimal supply temperature, and I would never have been able to actually find it in the data set. If we did not have these talks together, none of us would have actually found the true label for this project, because it was in that conversation that we realized that maybe we could actually create this hypothesis that either you deliver the optimal temperature or you have hydraulic limitations. So that's key, and if you work either on another company or you work with another department, make sure you understand just a fraction of their domain, because that's the center of the beauty. That's where magic happens. Understanding one fracture of each domain. Then when we do the proof of technology, we have these check-ins with their domain experts, so a team from their department or their company. And we need that in order to ask questions when we do the data analysis. So when I see something that looks abnormal, I have the possibility to ask them, is this normal, or why do I see this? And then they can pinpoint and say, well, this is normal, or okay, you're right. In this specific summer period, we actually did maintenance on that specific network path that you're looking at. So that's why data looks like that. That's because that specific area was not running because we were either upgrading the pipes or something like that. And then I can say, okay, that's fine. Then I will exclude that from my training model, because that data is not representative for how your normal everyday work is. So you need those check-ins. You need to keep communicating with them, not only for your purpose, but also so they understand what you are doing and they have a comfort in the model. This is also key not only from my perspective, so I can create the model for them, but it's also so they know what machine learning is, and they don't think when it's in production that it's just some magical black box, because machine learning is not a magical black box. It is just advanced statistics, and they need to understand how the model predicts. They also need to understand that, for instance, if they have these maintenance periods, the model might have some weird predictions because they use that data as input to create the prediction. And that means that if something is off in one of the paths, so one of the features that I get, then the model will also be affected of it. So they need to also be critical to those predictions that my model create. So in neurospace, we use very classic sprint. And in this a 30-day period, we have less than a week of a sprint. And it's simply to have these develop, test, learn, and then after every sprint, we have review, retrospective, and planning to make sure that we keep having this feedback loop and make sure that we keep going the right path and don't follow a path that then after 2 weeks you learn that that was the wrong path to take and you have to start all over again. So that's also highly recommendable.